Okay, grab your 3 worksheets, girls. And let's have a look at them. Which sheet do you want to look at first, and what do you want to start with? Which question?
The same worksheet that I worked with you.
Yeah.
Yeah. The very last question on that page.
A battery has an EMF of 24.4 volts.
Yeah, yes. The 2 on that page.
We did 2 the other day, so it's on on there right now.
Yeah. Okay. I had trouble with that one too today. Pardon? I had troubles with that one too. Like, I feel like it's better than the doorknob sometimes. Okay. I'll go back and watch it again.
Okay. I mean, we can go through it in a bit. Mary's not feeling good.
Yeah, she's sick. She had a really bad stomach, like her stomach's acting up. And I don't know if that's I don't think anybody else knows. Yeah, I'm not sure.
Okay. So question 4.
Yes. Yeah.
So,
I can get that one in first.
all right. So you have a 24-volt battery. So let's just draw it just to see what we're looking at. Set this up. Okay, so we have 24.4 volts on the battery. We have an internal resistance of 0.4 ohms. A load resistance of 5.7 ohms. And how much power? So let's just work through the question as is right now. So the first thing that we have done in all the questions is find out what the total resistance is. So 6.1 ohms, which then means that my current then is 4 amps. So 4 amps, 4 amps, right? So far, good, girls?
Yeah, I follow.
Okay, so now to get the power in the internal resistance, the load, and the total, you just take I squared R. All right, so 16 times 0.4. 6.4 watts. 16 times 5.7.
91.2.
91.2 watts. Add them together. So we have a total power of 97.6 watts. So that's, okay, so to answer the questions, how much power is delivered to the load? 91.2 watts. How much is dissipated in the battery? 6.4 watts. And then it says, so this changes the question completely. All right. If the load resistance, or sorry, it wants our maximum value, like our maximum power. So if the load resistance is changed to achieve maximum power, find the power dissipated in the load battery. So we do this all again. The voltage remains the same, but the internal resistance, it stays as 0.4 ohms, and the load resistance becomes 0.4 ohms. So there's the change. So then I have a total resistance of 0.8 ohms, sorry.
Can you move your camera down a little bit? I just can't see that far. Sorry.
It's okay. Okay. You can see the whole board now?
Yeah.
Okay. So I have this. So now I take 24.4 divided by 0.8. I get 30.5 amps. And it says, what is the, where is it? Maximum power dissipated in the load and the battery. It's the same for both. So 30.5 squared times 0.4, and we get 372.1 watts. For both. So the key to the important part of this question, is changing your load resistance so that it's equal to your internal resistance to create maximum power.
I changed it to my load resistance instead of my internal.
Right, okay. So, like in the textbook, that's what we went through. It says change your load resistance to the same as the internal.
I just had it backwards, that's all.
Okay, all right. Okay, take a look at your questions again. I just need, I need 1 second here.
Did you, like, I'm sure you did number 3. I can go back and try and find number 3.
I did number 3 yesterday, Daylin.
Yeah. I don't know why that works in my head. It's okay, not a lot through goes to my head. Holy, like that sentence.
Although, you know what? Oh no. Okay, well, hold on. Why don't I pull this up?
Like, I think
Oh, I didn't save it. I did.
That's fine. I'll go back and find it and see if I can try and make sense of it.
Okay, like, all that needs to do here, you need to do here, okay? You're given your voltage. What is it, 220 watts? Or is it or 22? 22 volts or 220?
220.
220 volts.
Like 500 watts.
500 watts. So I actually think I did this. I think I used 22 volts yesterday instead of 220. Anyways, so the first thing you do is you find your I. So take 500 divided by 220. And you get, yeah, I definitely did this different yesterday.
27.
Right. So current, the first thing we learned about current is it's in coulombs per second, right? It's the number.
Then you take it and multiply it by the number of seconds you have?
Yeah, in 1 day.
Yeah, so 24 times 3,600.
Right, so you've got 3,600 seconds in 1 hour, right? And then I've got 24 hours in 1 day because I want to find out how many electrons, and excuse me, and then I know that there are 6.25 times 10 to the 18 electrons. I'm talking to the board again. 6.25 times 10 to the 18 electrons in 1 coulomb. So all you're doing is you're needing to multiply those all together.
Okay.
Okay.
The only thing I messed up on was when I did my times. Like, I got the coulombs over seconds, but I messed up on the 3,600 times 24.
Okay. It happens. It happens.
That's funny.
As close as I could get.
You could do on the back page where you have to calculate the efficiency an electric hot plate.
Yep.
Number 6. And then number 7 too, please. Sorry.
It's okay. No, it's all good. That's what we're here to do. I'm just trying to, I just got to send this one quick email. This was
I'm going to go back and redo these worksheets again.
Well, it'll certainly help, right? All right, so you wanted the efficiency one. So number 6.
Yes.
Yuki. So let me kind of, all right. With efficiency, you have an amount of heat that's being output, okay? So the output is what you get from whatever you're heating up, like in terms of your electric hot plate, whatever's attached to the wall, let's say. Okay, so there's an amount of heat. So I've done this in the past where you take this is your hot plate. On top of your hot plate, you've got your kettle or your whatever your water is that you're heating up. So the heat output comes from the electrical part of it. So that's your output. Okay? The input that goes into the water, heat input, that's like the stuff that you're heating up. It's the amount required to actually boil it. All right? So your output of heat is your I squared R T over J. Your input of your heat is like your MC delta T plus your heat of vaporization. So your output comes from the wall to the element, and that's the output. That's what's required of you. All right? But you're only using a certain amount of it on your input to heat that water up. You're not using it in its entirety. So we want to find out how efficient your output is, all right, based on the amount needed to heat that up. All right? So taking that into account then, so an electric hot plate draws 12 amps. And I got a 120 volt circuit, which then means that my resistance in my wire is 10 ohms. Okay, so I just take V over R, or sorry, V over I to get my R. All right, and then I need a time. And the time's given to me is 10 minutes. So the math is great. 600 seconds. So right there, I've got all the information I need for the output. Okay, so let's just work with the output. So Q is equal to I squared R times my time. Again, I'm talking to the board. Times my time divided by my heat constant. Okay, so that's 4.19. I never put that in there, and I should. So that's 4.19 joules per calorie. Okay, so let's multiply that So the output that I'm getting from the hot plate that I'm using, the heating plate that I'm using, 206,205.25 calories. All right, now let's reset now, and let's find out how long it's taking to boil that water, or we know how long it's taking, but how hot that water gets. Okay, so right now I have 625 grams of water. So that tells me that my specific heat constant is 1 calorie per gram degree Celsius. My change in temperature is 20 to its boiling point, which is 100. So my change in temperature is 80 degrees Celsius. Now, because I'm evaporating, that means that I've got 150 grams of water that's evaporating. That means that I have to add heat to change from a liquid to a gas. That's called the liquid heat, that's called the latent heat of vaporization. So you need an excess amount of heat in order to change from a liquid to a gas. So I look in the back of the book. I don't know what it is. I can't remember. It's something 54. So I go to the back of the book here to find my latent heat of vaporization. 538.7. So for every gram that I'm evaporating, I need an excess of 538.7 calories to change the state of it. So now I go through and I've got Q is equal to MC delta T, 625 times 1 times 80 degrees Celsius, plus the excess, the 150 times 538.7 equals. So this is the amount of heat that's going to be required or used. So that's the amount of heat being used from the output in order to heat it 80 degrees Celsius, evaporate 150 degrees, or sorry, 150 grams. Okay, so 625 times 80 plus 150 times 538.7.
130,805.
130,805 calories.
And then you divide those two.
So to find out, yeah, so this is the amount of heat that it used out of your output. So to find how efficient it is, I divide that value by this value right here, right? And you get
63.28%.
I use more decimals maybe, but I had
63.281%.
no, I ended up, you're close, you're in the ballpark. I had 63.43%. So I took 130,805 divided by 206,205.2506. I'll use.
I didn't put in the 2.026.
Yeah, that's fine. Okay, so that's what we get there, 63. So where it all begins is right here. Your output is how much the wire and the element, how much heat is coming from the wall. Okay, or sometimes if you have a hot plate, all right, you've got just that base. Okay, now I don't know if you've ever seen those hot plate kettles. So they're actually all one piece, but the hot plate is on the bottom of it. So the output is this Q right here. The input is how much is used to heat the whole thing. to heat whatever's inside of it. Okay? And how much of that heat you use out of the total determines how efficient it was. Okay?
Okay, and I think using a diagram like that kind of made much more sense. Like when I think about it, like I'm calculating the efficiency
Yeah.
of the input output, and it just made more sense.
Okay. Perfect.
So when it asks for efficiency, you're looking for percent, right?
I'm looking for what, sorry?
A percent.
Yes, that's right. Yeah. All right.
Number 7, just below that, I think I can do now.
Well, okay.
That was in the book. I remember in that book.
Right. So you're looking for the resistance, or sorry, you're looking for the length. So to calculate the resistance in a wire, right? So there's a couple things. Sorry?
You have to use that chart, right?
Yeah, you will. So you have this rho, so resistivity. So the type of material it is. So in this case, it's German silver. We want to know what the length is. We need to find out what the cross-sectional area is. Well, they give you the diameter of the wire. So you need to use the diameter of the wire to find the cross-sectional area. All right. So you're given resistance. You actually just need the resistivity from the chart at the back. We're looking for L, sorry. So I've got L is equal to RA over rho. You want to do it, or you want me to leave it? What's your call?
I can do it.
Okay.
Yeah, I got it.
All right. Good enough?
Yeah.
Okay. All right. Any of the other questions that you want to see?
Yeah, I'm trying to find one on the assignment that I struggled with, but I'm trying to find an example somewhere like that book for you to do. Or on my papers.
Okay.
Yeah. It's the one where it asks for 2 dry cells are connected.
Okay.
But I'm pretty sure I just have to make that on my chart.
Yeah, that's, if it gives you the dry cells and it gives you either internal resistance or potential difference, they're looking for power likely, which is just that chart.
Yeah, it gives me like 2 dry cells are connected to this series that provide an EMF of 3.1 volts.
Yeah, that question's on the middle worksheet.
It's in here. I know it is.
It's question 7 on the middle worksheet. It says physics 300 worksheet 2 at the top.
Question 7.
Yeah.
That's the German silver.
No. Wrong worksheet then. It says it doesn't have the big number 2 on it. It just has a little 2. It's got the smallest handwriting on it.
These questions.
The physics guy that I took over for.
I like it. Yeah, you're right. Yeah, it's the exact same question.
Yes, it is.
So that makes my life a little easier.
That's what I'm here to do, Dylan. Make your life easier.
Personally, mine harder, but like, whatever floats your boat.
You just wait.
Life is actually pretty good right now. I'm not really stressed at all.
Huh. Well, that's good. I can't say the same.
Yeah. I don't know. Oh, I just want to say one thing.
Yeah.
You can try to top the name that Callie had. Try. You won't do it.
That's perfect. She'll be wanting to move here.
Yeah.
You should have given her Rory's experience on the farm, not a friend of Rory's experience on the farm.
What?
Said you should have given her your everyday experience on the farm, not a friend of yours experience on the farm. So she knew what it was really like.
What? We did tours, and then she fed a calf.
Yeah.
Then we went out to the freeze with lights. And what did we do?